Okay, mechanical vibrations. And this is the syllabus that was posted with some minor changes. As you see, the date on what was posted was, I don't know, January 3rd or 4th or something like that. And we have 2 weeks, as instructors, we have 2 weeks to change as need arises. For example, I add the list of GAs to this, updated office hours, things like that. This is incomplete. And some other issues that I'm going to discuss with you right now. The tutorial is in this room. The lecture is in the other room, which is starting next week. And this highlighted item is not what you had in your syllabus, draft syllabus. So I'm assuming that everybody comes to the lecture. That's wishful thinking. It's 8:30, as I said, winter time. I understand that, but that's my assumption. Everybody comes. However, I will record all the presentations if nothing goes wrong. Okay, I will try to record all presentation and post it on YouTube. So if people seriously cannot come for whatever reason, that's the other option. It's a good option, but then you can ask questions. I mean, obviously, you just watch what's there. Now, the link is the same channel that most of you had this summer, and taking the other course with me. And there will be a playlist there, which is called Mechanical Vibrations. So all the courses are going to be posted there one by one. But I was, just before you walked in, I said that I will not give you the copies of the PowerPoint. Okay, and the reason is I mentioned it. Is to protect you, in spite of the fact that you might say, I don't need protection, but mainly because, remember, the test and the final are open book, open notes, bring anything you want, I don't care. It's just no talking, no internet, that's all. It means no cell phone. But the thing is that there is no time to learn stuff there in 15 minutes. 3 tests, final exam is 3 hours. So you have to have done this thing before you come to class. I mean, you're in 3rd year, 4th year, most of you 4th year, you understand that. But still, you have to take your notes yourself, or you don't have to be here to do that. Watch the video, the stuff that's important to you to take note. Don't worry about taking note. Screen capture, print it later on. It's as if you took note. But if you do that 2 weeks before the test, a week before the test, there is not much time to do that. Every 3 weeks, almost there's a test. So if you do that, there's not time for you to learn and come and prepare for 50 minutes. Okay? Or if you say, that's okay, I'll borrow some other friends' screen capture documents. That happened. Last summer it happened. I saw people had screen captured or taken notes and copied it, multiple copies, given it to friends. Okay, I saw that. And I have no issue with it. It's just that if you read somebody else's stuff, particularly the day of the test, it's not going to help you. But anyway, this was not in the course syllabus. The reason I wanted to put it there is that I don't want people to say, this is mean. I mean, why can we bring everything, but you're not giving us the PowerPoint? I told you what. You make your own PowerPoint if you want. Bring it. Okay, everything else is the same as what's already there. Just about every 3 weeks during the lab, 50 minutes, and if there's no class after that, I'll give you an extra 10 minutes, okay? And even if there's a class after that, I'll try to convince the instructor, give me 10 minutes, we're running a test, okay? 1 hour on the material, done. Okay, now remember, in certain courses, material done depends on the material done earlier. Some courses may not be like that. If you take a course, I don't know, technical communication, test, but anyway, or I don't know, maybe you haven't taken engineering in society yet, but you will, most of you, all of you who are in 4th year. I mean, you go to 3 weeks classes, they say something, that's it. Learn it, come back and write a test on it, okay? And, but engineering and math doesn't work like that. You might might pretend that it works like that. We might think that we are so good that we can treat it like that, but it's not. Anyway, we'll come back to that. So these are the dates during the lab hour, and these are the list of the GAs that we have now. This person, you don't have it. I got the information last night and I fixed it. I'll update these as they come along. This is only a tentative schedule, and I say tentative because I have prepared all the lecture. Okay, at least I know what I want to say. But it goes lecture 1, lecture 2. But we have to see. It could be that lecture 1 takes exactly what I have there, or maybe shorter. It depends on how things go. Then that being the case, if I have 15 minutes left, 20 minutes left, I hope not. But anyway, if I do, I'll go to my second lecture. But when I update these things, the YouTube will tell you that today was lecture 1. Oh, but he went too quickly, so there is part of it from the other lecture too. Really doesn't matter what you call it. What I do is what you're responsible for. Okay. Now, if people decide to register in in 10 days because they thought that they were going to take this course, but they changed their mind, but they come and register for this course, okay, fine, there's nothing wrong with it. It's just that I don't make any special arrangements, okay? So if they missed it or you missed it, they missed it. They have to catch up, that's all. All of these you have, these dates are now filled in because what you had as a draft did not have these dates. I hope they're right. I'm sure they're right. If there are any questions, ask me. If there are any mistakes that you see, let me know. If you miss a test for a valid reason, and I'm not going to judge you, don't come to me, please, and saying that, I was sick or I was traveling. These are perfectly legitimate things. But go to the Associate Dean's office, discuss your case with the Associate Dean. If she agrees with your explanation, will tell me that, okay, this is a legitimate reason, so I'm going to take the weight of that test, pour it on the final exam. Okay? I think that's what it says. Yeah, I'm pretty sure down there. So, final exam. Good. We don't want to hear about fire alarm, but this usually applies. Yeah. Okay. Already talked about this. This course does have supplemental privileges. Some courses, the reason I say that, some courses do not have supplemental privileges. For example, if you failed your technical, sure you didn't, but if you did fail the technical communications course, you have to take it. There's no way to go and say, I want to write a test, makeup test, somewhere there on, on that subject. But this one does. I mean, most courses do, but the ones that involve design and things like that, design and design and communications and essays and things like that, they don't have it. You have to take the course again. But this one does. And I don't know, usually these are, they'll tell me when. I mean, let me give you, generally speaking, these supplementals, generally speaking, supplementals are done in December of that year. Now, most of you are fourth-year students, okay? So you will be graduating. You can't come December of next year because in principle you're going to be done in August. And I understand that. And if there are situations like this, we will give you early special supplemental exam. The associate dean will tell me that this is the situation. We'll give you special supplemental exam. No problem. Otherwise, whenever every other supplemental is, which is in December of that year. Although this doesn't apply, you probably know about it. It used to be supplemental was a bad deal because somebody already failed the course. Because this failure appears in the transcript and it's used in the GPA. So they decide to write a supplemental instead. So they write a supplemental on the whole course. In that exam, you get a new grade. That new grade stands Okay, the old grade stands 2, and it is calculated in your GPA. So supplemental was a bad deal unless it was absolutely necessary. It was better to repeat the course. I know you might say, it's easy for you to say to repeat the course. Yeah, but your grade point average is important. It should be important to you. So if that poor grade that made you fail uh, already brought down your average, why do you want to keep it there? If you think that you were good enough to get a better grade, well, put some effort into it and take the course again. But anyway, it no longer is like that. The supplemental is pass-fail. So that grade stands and is used in your GPA, which is not good. But the supplemental is either pass or fail. That's pretty much it. Okay, that was a good change that they made. Important, but usually people don't care about. If you have any questions, let me know. I will not have anything that gives you a mark in the last 7 days of classes, so I don't have to worry about that. Certain courses this doesn't apply to. And yeah, that's pretty much it. So it's very similar to what you already have, but with some minor changes that are made. Don't save. Okay. Are there any questions? Questions? We're good. All right. So let me see for a second. All right. So my plan today, as I prepared the lecture, was to discuss this syllabus, which I did, and we already chewed up 20 minutes on that, and then go to the rest of the stuff. Okay. So the course is about vibration and sound. These are closely related subjects, but they're not the same. And when I say they're not the same, sound is vibration. However, to do any stuff there, to understand anything there, you better know the basics. It's just like saying that, okay, I want to take a calculus course, calculus and algebra. I mean, these are related, obviously, but there's no way you can do calculus without having done algebra or trigonometry. So in order to do something in sound, you need to know the fundamentals of vibration, because after all, they are the same thing. The source of sound is vibration. Okay. Oops. All right. So this is all you're all familiar with, the shock absorber in the car. Yeah. So most of you will recognize this mechanism. There's a mechanism here. See that? Link 1, link 2, link 3, and the ground. So this is a 4-bar linkage, actually, that you did in the summertime and in machine dynamics class, except that there's a spring here. That changes the whole thing. As a mechanism, it's a 4-bar linkage. But putting the spring there, now you can find forces and, displacements and things of that type. Okay. Actually, that is nothing but a mass and a spring. Think about it. In a very philosophical way, that is a mass and a spring. Because after all, you put a load on that shock absorber, you sit on that side of the car, it goes down. So that's what springs do. You put a load, it stretches. You remove the load, it goes back to where it was. But what is the stiffness of that spring? Fancy, imagine trying to do, don't misunderstand that this spring that I'm drawing here is the spring here. The whole thing has a stiffness. Do not think that this spring is the one that I'm drawing here. It is not. This whole thing has a stiffness. It acts like a fancy spring. You put a load, it deflects. Okay? It's that spring that I'm thinking about. If it was that easy to put a spring there and pretend that we can do the calculation, we will be out of business. You'll be out of business. Okay, and the mass, of course, is, think about it as maybe the mass of the person that's sitting on that side of the car. And in fact, you might say, well, isn't the mass down here? It really doesn't matter, because imagine that I turn this thing around. Imagine that I turn this mass spring assembly around. The mass is on the top. It's the same vibration. It makes no difference. Absolutely no difference. Imagine that I took this thing, you will see, and put it sideways. There is no weight effect. There is no weight effect. But if you pull this thing, pull this mass and let it go, it will vibrate. And it does exactly the same thing as if it was vertical or horizontal. It makes no difference. What is important is not the weight, it's the mass. That mass can be hanging, can be sitting on the top, can be sideways, but the vibration characteristic of that structure is determined by that mass and the stiffness of the structure, whatever it happens to be. If it's a simple spring, okay, let it be. All right. Now, an ordinary person will say, okay, the vibration means this, moving back and forth, to and fro. Okay? Doesn't matter how you say it. Something that moves about an equilibrium point, as you see. Vibration is an oscillation. Now, what happens here, the reason that vibration takes place is that kinetic energy and potential energy are exchanged. Imagine a pendulum hanging from the top. You move the pendulum slightly to the right and let it go. You do this, everybody knows. So what happens when it reaches the top point? That's where the kinetic energy is zero. It is not going anywhere. Velocity is zero. Kinetic energy is zero, but it has the biggest potential energy because you raise basically the mass above some reference point. Okay? Now imagine it comes back to the vertical position. There, the velocity is maximum. But there's no potential energy. If you measure your potential energy from that bottom point, the bottom equilibrium point, there's no potential energy. So as this thing takes place, kinetic energy and potential energy are exchanged. Okay? That's what a vibration is. Exchange between potential and kinetic energy. Now, we are assuming that there is no loss in energy, because you know what happens here. If in a pendulum, for example, you let this thing vibrate for a long time, oscillate for a long time, eventually it stops. Why does it stop? Because at some point, the energy is completely lost. Okay? So we will do that, but in the ideal situation, this vibration takes forever without any loss in energy. Okay? Where do you think this loss of energy is coming from? Why does this thing slow down after a long time? Can you give me an idea? What does your common sense tell you? Why does it stop? Yes. That's one. Yes. Okay. Air resistance is one of them. Obviously. Yes. Internal friction. That's a good point. But you're right. Internal friction does take place. But also at the joints, there is friction. Most of the friction actually does not come from internal sources. Most of the resistance comes from that, if there's air resistance, but if this is done on the move, it will still slow down. There is no resistance there. But those frictional joints will actually take energy out. There is also this internal energy concept. For example, if you take a rubber band, something, I don't know, something not really soft, and you took it to the outer space, there is no air resistance. If you pull this thing and let it do this, okay, take a bar, take it to the outer space, pull it, and then let it go. There's no air resistance, there are no joints, but after a while, long time, this will just stop. And stop because of this. What happens at the atomic level, at the molecular level, and I don't know about those a lot, very little. That's why I didn't do chemistry. But anyway, it happens because of internal energy. All right. Now the sound is the same thing in the following sense. Suppose you have a loudspeaker and it's playing music. There is a drum there, right? There is a speaker drum. Does this. So there is a source of energy there. Somehow it's created by vibrating that, moving that diaphragm. That is sitting next to air. Now, the particle of air that is sitting next to that drum is not going to go run away and get to you. What happens is that slightly changes position of it, and that hits another air molecule, and that hits another molecule. So some disturbance propagates from the source, which was the diaphragm in the speaker, all the way to where you're sitting. And there, your ear, which is another diaphragm, will take that. So sound is vibration, but vibration of the molecules of the air not running away, not traveling. It's just that they hit the next guy. That guy hit the next guy and goes back to its original position. So that's, in that sense, sound has the same source. Okay. Sound happens because of three reasons. The source, vibration at the source object, speaker diaphragm, molecules of the air, and at the end, eardrum. Okay. Yeah, and by the way, not everything has to do with this concept. Is not only sound; it also applies to, for example, waves, electromagnetic waves, and things like that. But there is no air there that moves. So the same concept applies. Okay. Now, so air itself does not travel, but now we are concerned about sound because it bothers us. A buzzing sound, a high frequency, low pitch sound, it bothers us. So the vibration frequency of sound that we can hear as human beings is in that range, is in this range, 20 hertz to 20 kilohertz. Okay, 20 hertz to 20 kilohertz. Dogs can hear probably outside, I'm sure, outside of that range, or other animals with that. But human being is sensitive for the audible sound in that frequency range. Okay. If it's any faster than that, it's happening. Well, you can't hear it. You can't hear anything. But if it happens in that range, then obviously you're going to hear it. Faster or lower than this range. Okay. So, after you graduate from here, remember there's some courses were solid related, some courses were fluid related, or fluid related. But at the end of the day, when it came to doing things, you have to write the equation of motion. Sum of all the forces equal to mass times acceleration. So I don't distinguish between the fluid and solid. But there was a part of it where we didn't actually write sum of all the forces equal to mass times acceleration. We said sum of all the forces equal to 0. Okay? And that we called statics. First year. I don't know who taught you, Dr. Biswas, Dr. Chernayev, or whatever they taught you statics. Okay? It's the beginning of our knowledge of engineering and science. But dynamics is also a bigger version of this. Okay, so this statics is really part of dynamics, except that the right-hand side is not mass times acceleration. Either the mass is so small that we say, mass times acceleration, mass is very small, times acceleration is 0, or acceleration is very small. Okay, so the right-hand side we replace it with 0. Okay, so it becomes static. Now, vibration is part of dynamics. Okay, we can see that. Loosely speaking, things must move, okay, oscillate, vibrate, whatever. So vibration is part of dynamics, and acoustics or noise is subset of this vibration. This course is about vibration. But if you learned everything about vibration and you don't know what to do about it, that's useless. So you need to control the vibration. That is not part of this course. But in order to do anything meaningful, you have to control. That is, you have all taken the control theory course, right? Third year. Oh, is it fourth year? Because it used to be third year because there were two controls courses. Now there's one. Apparently everybody takes it. Now you will see that they will talk about the same kind of equations that we're going to see here, and they do things with it. Okay, but that's not my problem. Now, what can happen if vibration is not controlled? I'll show you a video. Do you recognize this? Ambassador Bridge? Really? Where is this? Okay, so we'll find out. Now, I have to admit that when I did my undergraduate education, I did it in pure mathematics. And I stayed away from anything that had to do with reality. Not even an economics course. Okay. The very first time that I ever saw something like that or heard something of this type was after I went to graduate school and applied math department. I was the GA for a differential equations course. Differential equations. Nothing, no vibration in sight, no force equal to mass acceleration in sight. But anyway, differential equation. So the guy who taught the course showed this on the screen for the student because it's closely related to a subject. It is actually that subject, which is called when you see something like that, and then bigger and bigger and bigger, and eventually you see what happens to it. What do you call this? And what thing's about? You go to an interview. It's not very far. It's less than a year. The guy asks you, "Can you tell me what do you know about this? Why did it happen?" Ambassador Bridge, imagine a twist like that. What would your answer be? It happened because of possibly resonance. Okay, we'll get to that. We'll get to that. You don't control it, you see what happens. Here's another one. Hawaiian Airline, I think it was Hawaiian Airline, yeah. Hawaiian Airline fiasco that happened in the air. That thing came off. I think one or two people, unfortunately, died in that accident. It's amazing that the rest of the people survived, particularly in that area. The source of it is vibration. That is not resonance anymore. Okay? We'll get there. So, I want to show you this. Okay, so let me stop that. We'll go here. Oh, hopefully this will work. Come on. Oh, you know what? Let me copy this. At home, when I was clicking on it, it would take you there, but I don't know. We'll see. Paste. And I don't know whether the sounds come now, but we'll find out. Come on.
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide. It lasted just 4 months. During construction, we see the steel girders, 8 feet tall, which were supposed to stiffen the bridge against bending. However, some up and down vibration was observed during the entire useful life of the bridge. Here's opening day. On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds. A professor of engineering went out to see what had happened. He's coming back, walking with some difficulty along the nodal line, which is the center stripe of the roadway. It's remarkable that the girders were this flexible. This is photographed at normal speed. However, a collapse was inevitable after a little more than an hour of this. The car had been abandoned earlier. No one was injured in the whole affair. However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge.
This is all. Now, by the way, after that thing, there was a press interview with the government of, this was Tacoma Narrows Bridge, the name of it, Tacoma Narrows Bridge in Washington State. And the governor very assuredly told the reporters and the members of the press that don't worry about it. We're going to make this bridge exactly at the exact same location, exactly the way we made the first one, and it's going to be ready in zone. And somebody said, well, it's going to fail exactly the same way that the first one did, which is true. There are design flaws. You do it again, it may not happen next year, it may not take 4 months, but it may take 10 years. Eventually, those design flaws are going to pop up in some other way. Okay, so let's move on. This one. So now, vibration is not always bad. I mean, you use these shakers to separate, for example, small blueberries from big blueberries, and other things, or small nuts from the big nuts. You use the shakers to kind of separate them together. Or another one is a rock crushing mechanism. For example, we did this thing in the class last. The version of it. It was a 4-bar linkage again. It crushed went back and forth and crushed the stones. We didn't do that part of it, but anyway, so vibration is not always bad. but it can also be catastrophic. And the one that you saw with the airplane was that fatigue crack growth, okay? Not the one with the bridge, but the one with the airplane was eventually traced down to fatigue crack growth. And what happened is that as the plane takes off and lands and takes off and lands, the pressure inside must be controlled. The pressure inside the cabin must be controlled. So they raise the pressure, they lower the pressure to make it atmospheric, raise, lower, raise, lower. So there is something that is changing over time. And if it is a tiny little crack, you have done materials course, those tiny little dislocation cracks under this very small change in load, pressure raising, pressure lowering down, raise, lower, under this load, cyclic load, that tiny little crack becomes bigger and bigger. It jumps from one rivet to another rivet. So there's a crack between the two rivets. And then again, from that rivet to the next one, and the next one, and the whole thing can fall apart. Basically, there's one gigantic crack going around the top between rivets. And this makes the whole thing fall apart. Okay, another one is machine unbalance. Machine unbalance is something that we're going to be doing in this course. For example, you buy a fan, and you put it on the table, and you let it run. You know what's going to happen. This table goes up and down, up and down. Now, it's so small that you can't see it. But if this was not a fan, it was some industrial machine which had, I don't know, gigantic masses and things like that, turning, milling machines and things like that, that is noticeable. And you should be able to see, first of all, to say how much force is transmitted to the ground. You don't want the whole force to be transmitted to the ground because you're going to feel it. It's going to come to you through the ground. You're going to feel it. So you want a portion of it to be transferred. And those things we're going to do. Machine imbalance is very critical, or critical, of course, and one of the things that they do in this course. Where is this? Now, I want to show you some pictures. Galileo was the very first person who actually worried about these things. Okay. I'll give you some names. It's good to know who did these things, at least partially. Newton, obviously, because vibration is dynamics. Dynamics is F equal to ma. Newton. Hooke. Where does Hooke come into the picture? You know who Hooke was, right? So can you tell me how Hooke comes into this business? What do you say? Because remember, yes? Yes, of the spring. Because remember, after all, when you try to do vibrations analytically, and of course experimentally too, you need a mass and you need a spring. We leave the damper aside. Damper is what takes energy away, or friction can be, for example, thought about. But forget it. Let's say that we're living in an ideal world. Spring and a mass. Hooke was responsible for actually talking about this decay of the spring itself. So it's going to come into the picture, whether we like it or not. He did not per se do vibration, but his contribution is in the form of defining or coming up with stiffness. Lagrange, Euler, and this guy Galileo was about 400 years ago. Newton was 300 years ago. Hooke was about contemporary with Newton. But this guy, Lord Rayleigh, that is popping up here, is about 110 years ago, 120 years ago. So it's fairly new. And who's this guy? Fourier. And all these names you're going to hear again. Any questions, by the way? Okay. So one of the things that you can't escape here is the concept of frequency. Okay, and the frequency, for example, you take a spring and attach a mass to it, either this way or that way, or put it horizontally, it doesn't matter. You take the mass, move it to another position, and let it go. You know what's going to happen. Or this, whether it's on the top or the bottom. So frequency is the number of these oscillations in 1 second. Okay? And the unit or cycles per second. Number of oscillations per second. And they denote it by hertz. This is fine, but most of the stuff that we're going to be doing when it comes to frequency, when it comes to doing some hand calculation and things like that, is not in this unit. It's in a different unit, which is not cycles per second, but it's radians per second, because each cycle is 360 degrees, right? But degrees is a layman's, ordinary person's unit of angle. The unit of angle is radians. So one cycle is 2 pi. 2 pi radians per second is the number of is the frequency in that unit. So let me say it again. In 1 second, how many cycles? Each cycle is 2 pi. Okay, so if you take hertz and multiply it by 2 pi, you're going to get the unit circular frequency, which is radians per second. Any one of these hertz, multiply by 2 pi, you get radians per second. Any radian per second divided by 2 pi, you get hertz. So these are related, but yeah. Now the period of oscillation is these peaks, because we know that after all it's oscillating. Between two peaks, consecutive two peaks, how long did it take? Well, that's called period of oscillation. Now, people usually call it T. If you have things in hertz, then all you do is do 1 over hertz. 1 over hertz, what's the unit of it? 1 over cycles per second is going to give you second. So if you have this frequency in hertz, just invert it, 1 over it. You're going to get the period. If you have the unit in radians per second, okay, then you multiply by 2 pi, obviously, because you multiply hertz by 2 pi to get radians per second. So this is very common source of mistake. A very common source of mistake for everyone. They don't pay attention to what is the unit of this thing that either it's derived or they're mentioned, because it affects the, I mean, if you don't take the units into account, you may be doing everything wrong, including finding the period. Okay, so period of time is period duration of time in 1 cycle between 2 peaks is 1 cycle. What is that time? So you can see here, for example, this is period 1/3 of a second, etc., 1/6 of the second, so on. So period is 1 over frequency as long as frequency is in hertz. If not, okay, then fix it, okay, and use it. It's still 1 over frequency. It's just that you may be off by a factor of 2 pi. Okay, so I'm not going to elaborate on these things, and because I haven't decided exactly how the tests are going to be. There will be some, I mean, obviously maximum one hour is maximum 1 hour if you're lucky. There will be some hand calculations. Usual, do this. Here's the problem. There may be some multiple choice true false questions. So it's perfectly legitimate to say, here's the frequency, what is the period? Now, if you haven't done your homework, I don't mean literally your homework, your work, it's going to be tough. It's very easy to make a mistake. So move on. When you take one of these cycles, it looks like a sine, but it doesn't have to be sine, but I'm drawing it as a sine. There is an amplitude, okay? And when it comes to amplitude, plus or minus doesn't matter for us, okay? And so there's the amplitude. And let me see, maximum extent of repeating events. Okay, and let me show you something. So you have this machine, this fan that is going up and down on this table, and you want to find, for example, what is the displacement of the table. So this goes up and down, the fan goes up and down. The reason is that fan is not a disc. If it was a disc, perfectly round manufactured disc, as it turns, there won't be any oscillation. None whatsoever. But it's not a disc, number one. And even if it was a disc, it would not be perfect. There's a tiny little chip there, or a little hole there, or just by manufacturing reasons, some part of it was a little bit heavier than the other one. Or the place where you actually stuck that disc into the center of rotation may not be exactly the center of mass of the thing. So anyway, so I'm saying that even if it was a disc, the table will go up and down. Definitely for a fan, it will go up and down because there's an imbalance. Okay? Now, you want to know what the, for example, what the displacement of the tabletop is. Okay, so these days they go and get an accelerometer, stick it to the table, and they measure the acceleration, not the displacement. You can measure displacement, but accelerometer measures acceleration. But if you have the acceleration and you do your math backwards, Dr. Altonoff, backwards, you're going to get your velocity and you're going to get your displacement. The moral of the story is that you use a vibration pickup sensor, for example, accelerometer, to get the displacement as a function of time. It looks something like that, and this is nice and clean. In a real life situation, it'll be like this. There's no form to it like that. So this is time variation of displacement. It may be useful to you. I'm not saying it's not useful. All I'm saying is that in a real life situation, it's not that clean. So just looking at it is totally useless. Just looking at it. But you can display this information in the frequency domain. The frequency domain is that it shows you two spikes. Okay? Or many spikes. It doesn't have to be two, some spikes. It says this time variation is made of, in principle, several sines, for example. This is a sine curve. Several sine curves or cosine curve. Each of them of that frequency. So you actually look at the frequency content instead of looking at time variation. I'm not saying time variation is useless. All I'm saying is that many times you don't worry about time variation, you worry about frequency vibration, frequency content of the response. Now, I don't know whether I can show you the video, but it may not be necessary. So suppose we have two motors sitting there, my fans, and they're turning. And I put that accelerometer on the corner of this table and measure the acceleration. And if you look at the time variation, of what you're recording, don't let it fool you. This is not real. Real stuff is going to be jagged. Totally useless if you just try to do that. That is made in that particular case. If you can show, or you can use your device to show that the frequency content is actually made of two frequencies, and I've drawn it. If you add these two functions, 20 kilohertz, 40 hertz, and 50 hertz, add it, you get the thing on the top. Okay? So, same diagram. It's the same graph, except that notice the way I'm displaying it is a little bit differently. The amplitude is up. The horizontal axis is time. It's exactly the same graph, blue graph, or decomposed one below it. It's exactly the same thing. I haven't done anything. But there's an additional frequency axis that I've introduced here. This graph is exactly that graph. I haven't done anything to it yet. Now I'm going to say, okay, when I look at that, the red one, I know that it's 40 hertz. Just literally go count. Literally go count 40. And the other one is 50 hertz. So I can I shifted it to 40 and 50. You see that? Now, instead of being in the plane in the back, it's at 40 and 50 hertz. Just look at the red one. The red one is on the frequency axis at 40 hertz. The green one is at 50 hertz. All I've done is separate these two graphs from each other. Before, when you were looking at it, they were both sitting on the same axis. Now I have separated one on the 50 hertz axis, the other one in the 40 hertz axis. Okay, so exactly the same thing, except I've turned things around. I'm looking at it from differently. Exactly the same thing. And let me turn it a little bit more. And a little bit more. This is what you're going to see. If you looked at this top graph, if you looked at the top graph down the time axis, you will see two curves. On the side, what do you see? Just a spike. Because the curve is coming towards you. You can't see it. This red curve is coming towards you. When I look at it from here, all I see is the amplitude at 50 hertz. And the green one, that green one is coming towards you. And if I look at it from here, all you see is a green spike 40 hertz. That says it all. Anything that you want to know about your machine can be deduced from this information. You don't have to see signs like that, because all that's important is how often this thing repeats and what the amplitude is. That's what I mean by looking at frequency information. When you buy an accelerometer and you attach it to something that records the data and shows it to you, you have a choice, seeing it in the time variation or frequency. If you look at the frequency with the frequency option on the display, you just see this. If you look at the time, you see that original blue curve that is not even here. I just basically showed it to you as a green one and a red one, summed up. Now, we still have it on time, so that's good. So, what do we do here? I mean, I'm sure you've seen sitting on the window of the airplane and see this wing going like that. See, that's scary. First of all, doesn't mean it's going to fall apart, no, because they took these things into consideration when they designed it. If they don't, you end up with a common narrow split or that other situation. Wait a minute. Okay, so vibration. You're looking outside the window, you're seeing this guy vibrate, the wing vibrating. That scares you. Maybe the rudder, what's that thing? Is it rudder at the end? I can't remember the one that goes like this. Aerospace, any aerospace students? In a boat is a rudder, but I don't know, maybe that thing that makes the yaw motion. Anyway, the thing is that you're not even seeing that. That doesn't bother you. All you're seeing is the wing. Okay, so we concentrate on the wing. The thing in the back may be even more dangerous, but you're looking at this. So it is a vibrating system. It has a mass. Well, I have to make some assumptions. Okay, should I take this piece into account or not? Probably you're going to say, oh, the thing that makes it fall apart is probably this piece. Because if the cantilever beam, after all, this is a cantilever beam. The engine is here, cantilever beam. In deformable bodies, where was the maximum stress under ordinary circumstances that you worried about? What did Dr. Green ask you? Find the maximum stress. Where would you look at? What is the formula? MC over I. The place where the M is the biggest is going to give you the biggest bending stress. Where is M the biggest? If I'm holding this weight, make the cantilever beam to bend like that, the biggest stress is right here, right there. So what happens after that? much. Okay, you don't want this. I threw away that piece of an assumption. The mass of an engine. I mean, this is not a single little dump bulb of mass. It's something 3 meters, 2 meters, or whatever. I'm going to make an assumption that this is a point load, as if I had a mass, a point load at a point, and a spring. Well, where the heck is the spring? I don't see any spring here. I don't see anything that looks like a spring. That cantilever beam acts as a spring. If you put a load on it, it's going to bend. Isn't that what a spring is? You put a load, it's going to bend down. Change the load, the amount of bending is going to vary. Remove the load, it's going to go back. So it is a fancy spring. And for a beam cantilever, you know if you put a force at the end, how much it's going to deflect. You have it in your book. It's one of those things that you should never forget as a mechanical engineer. FL cube over 3EI. F, force that you put, L, cube over EI. E is steel, aluminum, etc. I is the cross-sectional moment of inertia. So if I take the F apart, the stiffness of that fancy spring becomes EI over L cube. Displacement equal to FL cube over EI. Force over displacement is going to be EI over 3L cube. So what I'm saying is that this can be modeled very crudely as a mass spring system. The spring stiffness I gave you, and the mass, whatever the mass of that object is. These are all approximations. And based on these two numbers, you can find out this wing that you're watching, how much it goes, not how much, but what is the frequency of oscillation. Based on that, you can get the period of oscillation, etc. This is a very crude way of doing it. There's no doubt about it. But that's the kind of thing that we do in most of this course. So we are essentially replacing a very complicated structure, the beam, the wing, with a mass, with a spring and a mass, and we're pretending everything is governed by this motion. Now remember, this scares you, but it may be doing that that you don't see. That may also be important. It may be torquing, okay? Or it may be doing oscillation in this direction. The one that scares people most is the going up and down of in transverse vibration. It does this, it does that, but we're going to ignore it. We're going to say, oh, my concern is that guy. Okay, so, but there are more sophisticated ways of doing it in this course, and we will do a little bit of it last 4 weeks. But you do more work, as simple as that. And if you can't do nothing, you get a finite element package. You spend hours doing the wing and the engine and things like that, and ask for frequencies, natural frequencies. We did a couple of problems like this. Natural frequency, and you're going to spit out the number. And that number, the smallest one, is going to be the thing that you get very good result by 1 degree of freedom system. Okay. All right. Here, essentially, I have thrown these pieces away. I've done a mass here and a beam. Okay. It is possible to do other things. Now, so I already talked about these things, and although there won't be the full model, it's going to be just about impossible to do manually. You can do it on computer, and they do it on a regular basis on computer. With CATIA, which is a terrible FEA solve. Boeing and Airbus, and the first attack on the design is using these packages, basic packages. Okay, so basically what I have done is now this particular thing that I'm showing you, it looks like I just did the end piece. Okay, I did the end piece, another cantilever beam. It looks like it. I don't know. This piece is the beam. This is a beam. That was a beam. The one that I described to you with the two-engine aircraft was this piece. But you could have done it for that because that's also a cantilever. Right there, right there. Cantilever, beam, mass. Okay. So basically, we modeled as a spring and a mass. This mass can have motion up and down. That's what scares me. It can have rotate, spins. Okay, spins like that. That's going to give you the yaw motion of the entire wing, and it can, you'll actually go that way. The wing can go that way. That doesn't bother me. I can't even see it. Oscillates like this too. But anyway, these are things that we do. Oh, some of these are taken from Dr. Novak's course that he has offered over the last few years. You take a car. Well, the car has 4 wheels, right? And if you took, for example, the front two and lumped it together, kind of squished it together. There's a tire here, a shock absorber, etc. If you squish it together in the front or in the back, you get what is called a single degree of freedom model of the car. So if you do things like this, all you're carrying is vibration like that. You're sitting in the car, this car goes on a bump, and it goes like this. That's all you're caring about. Okay. If you do the front and the back lump together, the front ones lump together, you see one of these. The rear ones lump together, you see another one of those, and put it together, you see this. This is a half car model. That's called a quarter car model. This is a half car model. What happens here, over there, in this situation, half car model, you can also do the bounce and pitch. As you go over a bump, that top, the frame of the car, can also go like that. Not only go up and down, but it also can bounce and pitch, bounce up and down. You cannot do it with that, because that's a point mass, essentially, I'm assuming. So you get the information. The more assumptions you make, the less reliable your information is. But it could be that, I can show you, that the first round of design is all these very crude models. You don't even know what you want to do. So you don't go and make the whole thing on a software, like a software, and then decide that this shouldn't be like that, let's go change it. Anyways, so more realistic is the four-car model. You can do bounce and pitch, up and down, and the yaw motion, which may not be doable with other things. Okay. So I think I showed you these. One of the things that's going to be extremely important in this course is the number of degrees of freedom associated with a model. For example, the first one that I showed you, the very first one that I showed you, we still have about 5 minutes and I can finish that. The first one that I showed you was a 1 degree of freedom motion of the car, up and down. The next one that I showed you was a 2 degree of freedom motion. For example, you can think about motion of the front wheel, motion of the rear wheel, or you can look at the frame of the car, up and down motion, and the bounce motion. It's the same thing, 2 degree of freedom. The other one was 4 degree of freedom system. Okay. In reality, if you have a situation like that for the wing of the aircraft, if there are 2 engines, 2 on this side, 2 on that side, there's no way you can do it with 1 degree of freedom. That wing on one side, engine 1, engine 2. This is a 2 degree of freedom system. We're going to do that in the last 4 weeks of the course. Okay? 2 masses, 2 springs. The number of masses and number of springs has nothing to do with it. What is important is how many degrees of freedom does this have? Okay, let me see if for the next one, Just 1 second. I think that next one is not a big deal. We already talked about all the different aspects of it. It's not an issue. Now, if you go on YouTube, there are lots and lots of courses and people talking about something like this. There's going to be another one when I post mine. The ones that if you are interested, if you don't understand what the hell I said, because I'm explaining it in a poor way, fine. Well, obviously you have to go to a book. You don't have the mandatory book, but this is what I'm using for the source of most of the stuff in this course, Inman's book. You can go to a book if you want, or you can go to some good set of lectures. MIT, excellent. If you feel you don't need that, I mean, I'm just not mandatory. I'm saying that if you don't like me, when I say go ahead, at least read the book or talk to someone or go to these. There's 3 of them that I'm going to suggest to you. The other one is University of Akron, and this is at Florida International. And there are probably 500, 1,000 more things like this. Basically, we are rehashing stuff in the last 300 years for you. Nothing is new. Yes. This is the first time I'm doing this vibrations course. No, I don't have. Main book, right up there. And there are a zillion other books like it. These are some. Last thing that I want to tell you, this is very important. This is not the math course, but you cannot get away from the math. Not complicated math. It's the stuff that they taught you. For example, in differential equations. Little bit in linear algebra. Most of it's in differential equation. Now, what I'm going to do, because we wasted 20 minutes, the stuff on the next transparency, on the next plot, I'm going to do a video segment on it, okay? Because I want to remind you of some of these things that you saw in your differential equations course, and you said, this is never going to come back to me. It is. Differential equation. Look. Remember that? High school. Well, actually, we didn't do differential equation in high school, but if this was x squared, ax squared plus bx plus c, this would be high school. Okay. And because a single degree of freedom that we discussed today for the next 7 weeks, 8 weeks, is this. Second order differential equation, constant coefficient. M is the mass. C is the damper. And I forgot to put there. Sorry. This is all garbage. All wrong. It's going to be Cx dot. I'll fix that. Plus Kx. Garbage. Okay. So this, how do you solve those 3? And the different ways you get the solution to those. This was one of the easiest things that we did in differential equation because there was a recipe for it, and you followed the recipe. I don't want, as a review, I'm going to make a video on this last transparency and post it along with the lecture notes, of course. I think this is it. Yeah, pretty much. I was on time actually. That was good. We're done. So see you on Tuesday, right? Tuesday.